All right, so we finished up the material that you're responsible for yesterday. Today we're not going over anything new. We're just gonna kind of go back through uh, what's going to be on your test coming up next Tuesday. Again, it's our last test, whether you call it the final exam or test four or whatever. It's next Tuesday, August 4th, 8 to 9:30, and I probably will make it available a few minutes before 8. So if you want to get started a little bit early, you might want to check in about, I don't know, 7:45, 7:50, somewhere in that range. Uh, you can start the process. And regardless of whenever you do log in and actually start, you got 90 minutes from the time you actually start taking the test. Whenever the test opens, you have 90 minutes from then. Just like on the previous test, you had 60 minutes from whenever you got through the honor lock verification and started the test. This time you had 90 minutes from whenever you start. The process is the same. You've been through it 3 times now, so hopefully everybody's expert at that now. Should be old hat. I'll send you out an email sometime, I don't know, across the weekend or a Monday for two purposes. One, just the last reminder about the test on Tuesday, and two, I'll resend that procedure again just to refresh your memory in case you've forgotten. But I'll try to send that email out Monday at the latest, just to remind you. So this test, as I said, you got 90 minutes. There's going to be 5 problems. So actually, time-wise, you should have a little bit more time. I think the last 2 tests you had 4 problems in 60 minutes. So you got one more problem, you got 30 more minutes. So if you can't complete the test in 90 minutes, it's not because you didn't have time, it's because you didn't know what to do. So you should have time to work those 5 problems. And you'll see as we go through here in just a minute. I mean, there's 5 sections that we've gone over since last test, and you're going to have one problem from each of those sections. And so that's what we're going to do. I thought today we'd just kind of go back through each of those sections, and again, how long we stay today will a lot depend on you and like how many questions, what kind of questions you might have. So I reckon let's just start. We'll go through the first thing we did since last test was chapter 11 was beam design. So just real quick, kind of give you a couple of highlights, remind you of what we did. Again, this was the beam design, and one important thing, hopefully you got when we did this, is that you size the beam to satisfy bending. So you choose the size of the beam so that you don't exceed the allowable bending stress. And if it's a custom design, you're not using one of those standard size beams. Remember maximum bending stress. Use this formula, MC over I, where C here is just the maximum distance you can get away from the neutral axis. That's what the C is here. And so you size the beam to satisfy your bending stress, and then you check to make sure you haven't exceeded the allowable shear stress. So then you want to check if the maximum shear stress for that beam you just chose is less than or equal to the allowable. Now, a couple of ways we can do that. It sort of depends on what type of cross section we have. If you've got a rectangle, if your cross section is rectangular, then Again, you don't have to, but you could use this formula. I might save you a little bit of time. 3/2 V over A. If we're doing one of those standard I-beams, right, here's where I told you you could use that approximation. And so to get tau max for this I-beam, you can just do, again, whatever the maximum shear force is over the area of the web. Right, this being the area of the web. You can do that. You don't have to go through the formal VQ over IT. Now, if you got something else, then you would have to use the VQ over IT. But as you saw from working if you work the suggested problems in the book, most of them are one of the first two types. You either got rectangular cross section or choosing one of those standard I-beams. Let's see. You do need to calculate moment of inertia, and same thing applies as for the last test. I expect you to know the moment of inertia for a rectangular cross section. All right. Got some base B, some height H. I expect you to know that the moment of inertia about the axis through the centroid for a rectangle is 1/12 base times height cubed. Any other area, shaped area, I would provide you with the table that's in the back of the book, right? But again, if you've been working the suggested problems, you've seen lots of either rectangles or a combination of rectangles, and you should have used this formula a lot by now. That one I expect you to know. Anything else would be provided for you for as moments of inertia go. And I reckon just the last thing I'll mention, if you are doing one of those standard size beams, where we choose a beam from that table, remember we define this thing called the section modulus. So the required section modulus is you just take the maximum moment, divide by the allowable normal stress, and that'll tell you the minimum section modulus you need, and then you go to that table, which is in Appendix B. That'll be provided to you, and you would, again, select the beam that has a section modulus at least this big. But to be good engineers, remember we're choosing the lightest one. So that's not always the one closest to that required section modulus. You might can find a little bit bigger, stronger beam that actually weighs less. And so if that's the case, that would be the better choice. And of course, to get your maximum shear force and maximum bending moment, maybe should have started with this, but you got to know how to draw shear and moment diagram. So to some extent, chapter 11 here kind of basically you got to know how to do the stuff from chapter 6 and 7 to do this. So it kind of covers a good bit about beams and bending stress and shear stress. So maybe before we go any further, if somebody's got any question you want to ask related to beam design, then we can maybe go ahead and address that here. Everybody good with beam design then? All right, well, we'll move right along. We might get through early today. The next topic, I suspect most of you probably are good with, and that was, we went to chapter 8, and that first section, chapter 8, that had to do with pressure vessel. And we looked at two. We looked at a cylinder. If you got a cylindrical shaped pressure vessel, we saw we had normal stress in two directions, the axial direction and what we call the circumferential direction, or we shorten call it the Hoop stress. And so we came up with these formulas. The normal stress in the axial direction, sigma A was PER over 2T. The hoop stress was just PR over T. And note here, the hoop stress is twice the axial. My A doesn't look real good. All right, so the hoop stress being twice what the axial is, if you're designing a cylindrical vessel, the hoop stress is going to govern and determine the design of that tank, because again, that stress is twice what the axial is. All right, so the other shaped vessel we looked at was a sphere. And for the sphere, it was nice because of the symmetry involved. The normal stress in the two directions are the same. So the normal stress in a spherical shaped pressure vessel is the same as the axial. It's PR over 2T. So those formulas you need to know for normal stress in a pressure vessel. Any questions anybody have related to pressure vessels? Okay. Then we'll move along. We got two of the three down. Again, you'll have one problem from beam design. You'll have one problem related to a pressure vessel. Right. The next section, the next topic was also in chapter 8. This was where we did the combined axial and bending. And if we're bending about both axes, we have this formula, P over A minus my over I. And here that M is the moment about the z-axis. And the I is the moment of inertia about the z-axis. And then plus mz over I, where this is the moment about the y-axis. Z is the distance away from the y-axis, and divided by IY. Now, if you're using this formula, right, this formula is based on the following sign convention. So this is plus, this is minus, this is plus, and then you put in appropriate signs for your moments, your y's and z's. And the signs on the y, the z's, and the moments are based on this sign convention. And remember, we talked about when you do have combined axial and bending, the neutral axis is not at the centroid anymore, but we keep our coordinate system at the centroid. We don't move the coordinate system. It would stay at the centroid of that cross section. And again, a positive P would be a axial force in the positive x direction. It's going to be causing tension. The signs for the moments are based on right hand rule. So a positive moment, mz, would be one that bends in this direction about the z-axis. Again, put your right hand with the thumb in the positive z direction your fingers go. That's a positive moment about the z. If it's in the opposite direction, you would plug in a negative moment into this formula. And then similarly for the y-axis, a positive moment about the y-axis would be a moment that bends it in that direction about the y-axis. Again, based on right-hand rule, thumb in the positive y, direction your fingers go is the positive moment. So if it's in that direction, you'd plug in a positive my there. If it's in the opposite, you plug in a negative. And then again, y and z, if it's in the positive z direction, you'd put in a positive z. If it's over here in the negative z direction, you plug in a negative number. That's a good way to do it. I did mention that if you don't like going through the formal sign convention, and you can actually see what's going on, and a lot of this is personal. Like some people see and visualize better than others. But I told you that it was also acceptable if you wanted to not use the formal sign convention, right, and just think of it as plus or minus each of these terms. And you're just going to put in plus or minus based on whether that force or either one of those moments is causing tension or compression at that point that you're calculating the stress. So again, here, plus or minus would be based on, is it tension or compression at that point? And you're just going to enter the magnitudes for, again, the y, the z, mz, my. Right? You're not going to assign a formal, is this in the positive direction, negative direction? You're just looking, the direction that moment's acting, is it causing tension or compression? And you just put plus or minus based on tension or compression. Either way works. Again, hopefully, if you've been working some of these problems, you've figured out which way makes sense to you. And that's what I would say, go with it. If you can look at it and easily tell, oh, well, that's tension, that's compression, and you want to do it that way, that's fine. But if you get confused or you're not confident in that idea, then use the sign convention. Okay, use this and plug in the plus or minus for the moment or the y or the z, and you'll get the right answer that way. All right, that's basically what that section involved. Was you had members that were being subjected to an axial load P, as well as being subjected to moments, either about the z-axis, the y-axis, or both axes. So that's about all you got for this section. Any questions related to combined axial and bending? Remember, we didn't do the axial, bending, and twisting. We deleted that, so none of those suggested problems involved twisting as well. So if you see the example in there where they do the twisting, you can not worry about it. You're going to have one problem where you got a combination of an axial load and bending about one or both axes. All right. Anything related to combined axial and bending? Okay. Well, then the next thing we did, we moved to chapter 12 and we went to beam deflections. And the first thing we looked at was in the first couple of sections in chapter 12. This is where we looked at solving these using what's called the double integration method. Which basically was using the method of sections to go out to some arbitrary location X along the length of the beam, cut it, determine what that internal bending moment was as a function of x, and then you take that moment function and you put it in this differential equation. And then, in order to solve that differential equation, you just had to integrate twice. And so you integrate the first time, it would give you the slope or the angle. You'd have dy dx is equal to 1 over ei. Remember, we're assuming e and I are both constant. Right? So we can always pull them out. We don't have to integrate those. But don't forget to put them on there. As I see students all the time, they'll leave that off and they'll just integrate the moment. And it's wrong if it doesn't have the 1 over ei there. But you just integrate that moment, and then you'll get a constant of integration. All right, that'll give you the equation for the slope. You integrate again, you'll actually get the deflection or the displacement, or the equation of the elastic curve, as he calls it. So you just integrate again. So you'd have whatever you got when you integrated, just integrate it again. The constant, when you integrate with respect to x, you just get the constant times x, and then you'll get a second arbitrary constant of integration. And then it's a matter of using your boundary conditions and possibly, if necessary, the compatibility condition to solve for these constants of integration. So then you just use your boundary conditions, I'll say and or compatibility conditions to solve for your constant. And our boundary conditions here are the fact that if you have a support, it prevents it from moving. So you know the deflection, or you know y would be 0 at that x value. It's possible, like if you got like a cantilever beam, you got a fixed support, right? It prevents it from rotating, so you would know that the slope would be 0 there. And so you could set the slope equal to 0 at that particular x value and solve for those constants. Now, that last example we did in this section, we had to cut it twice because remember, if the load changes, your moment equation changes. And so you'd have to get a second set of equations, and that's where the compatibility would come in, where those two sets of equations meet. They would have to give you the same values for slope and deflection, right? But that's the process. Now, again, some turn out to be longer than others, but you approach it the same way every time. All right? Do method of sections, get your moment equation, integrate it once to get slope, integrate it again to get deflection. Just don't forget to put your constants of integration. I see those get left off quite frequently. Any question about getting beam slope and deflection by using the double integration method? I'm not real acquisitive today. So the last section, hopefully, what we did yesterday, you thought was pretty easy, hopefully. Okay, this was where we did the method of superposition. And that's where we used that table. So that table, I think that was Appendix C, if I remember right. I'll look over here. Yeah, that's Appendix C. That will be provided to you. So here's where you got a beam with more than one load acting on it. And you just break it up and you get the slope or the deflection due to one load. get that from the table, and then you get the slope and or the deflection from the second load from the table. If you got 3 loads, same thing. And then you just add those together. And so whatever the slope for load 1 plus the slope for load 2 will give you the slope for the 2 combined. And same thing for its deflection. But that table is provided. Just be careful. Remember, the table uses V and I used Y. So I don't know if you've been using Y or V, but just be aware of the notation difference. And also in that table, if most of the loads in those tables, the forces are acting down. And so, the positive deflection is up. So you see a lot of negative sign. But if you had the exact same load, but it was acting up instead of down, you just change the sign to a positive, right? Because it's going to cause it to deflect upward instead of downward. And positive Y is up. Any question about superposition, what we did yesterday? That's it. That's 5 things we did since the last test. You're going to have one problem from each of those on Tuesday. Anybody got any questions? Nothing? Oh, we got one question coming in. Let's see. Actually, several questions came in all at once. Let's see. First question is, will I tell you whether to use double integration or superposition? Yes, because I want to see if you know how to do double integration. If I don't specifically say that, then you could use the table in superposition, and it kind of defeats the purpose. So yeah, I'll specify double integration or superposition. Next question. I don't think you'll be able to print out the table. The question is, will we be able to print out the table or have to look at it on the screen? I'm pretty sure, if I remember right, HonorLock will not let you print. So I think that's the case. I'm not 100% sure, but from what I remember when I went to the HonorLock training, I'm pretty sure I remember that right, that it blocks you from printing. Now, I suppose if you tried to print it and it lets you print it, then that would be okay. I don't have a problem with that. I'm thinking HonorLock is going to not allow you to print it, and that you would have to just look at the table on your computer screen. That's, again, my best answer I got for that. Okay, so we had 2 questions. Anything else? All right, we could just sit here in silence for another 20 minutes or so, or if nobody's got any other questions, I will end the session. I will tell you, if you do think of something or have a question, between now and then, start by sending an email, and then we'll see again, depending upon what the question is, whether we can address it and answer it by email, or whether or not we'll need to either talk on the phone, or I could set up a private one-on-one WebEx session or something. Just keep in mind, between now and then, I'm not can guarantee how quick turnaround you'll have, because it's not like I'm going to be sitting here in my office between now and Tuesday just monitoring my email constantly, waiting for your questions. I'll check periodically, a couple times at least a day, to see if you've sent me anything. So just keep that in mind and have a little patience. If you think of something like this afternoon, you send it to me. I'm going to be cutting grass this afternoon. I may not get it until either later this evening, or it may be tomorrow morning before I get it, but I'll get it and respond. Just be patient and don't expect, super quick turnaround. Anything else?
I have a question about one of the chapter 11 homeworks.
Okay.
Um,
Which
so
one?
what, it's number 5 or
11.
11.1, 11.2.
Okay. I'm looking at it.
All right, so I think the books had used 12 a W12 by 16, but I found that W12 by 14 was closer to the S value, and the uh, shear stress was still lower or low enough that it was
Okay.
allowed.
Okay, but hang on just a second. Again, you're not necessarily going to always use the one that's closest to the required one. It says choose the lightest one that will work. So let me go back here and look at this table. I gotta find it. Index B. These are English units. Okay, so hang on just a second. And this was 11.5. All right, now tell me, what was the required section modulus that you calculated?
It was 15, I believe.
I couldn't hear you.
15?
15. So this was 15 inches cubed.
Yes, sir.
All right. So let's see. Let me go. I think I have a copy. All right. So yeah, here's a copy of the table. That's these are English units, and so this is starting with the little beams, right? When we did this, we were wanting the lightest one, so I would start with the smaller ones and go up rather than start with the biggest, heaviest one and go down. So we're looking for S required here of 15 inches cubed, right? So we're not necessarily, again, going to choose the one that's closest to 15. We want to get one as close to 15 as we can, but we might find one, again, that's a little bit lighter, that's a little bit bigger than the one closest to 15. So let's see. So I would start here and go up till we find one that's 15. So this is a 16.7, so that would work, right? But that thing weighs 25 pounds per foot. So let's go to the next group and see what the first one of those that's bigger than 15. That's 20.9. It's only 24 pounds per foot. So even though this S is closer to 15, this is the better beam, right? Because it's 1 pound lighter. That means it's cheaper. Now that may not be the best one. Let's go up to the next size. And so I go up to the next group, the W10s. And here we got an 18 by 8, right? And it only weighs 19 pounds per foot. That's better than 8 by 24. And if we go up to the next size, I got a 17.1 is the first one bigger than 15. That one's close, 14.9, but it's got to be at least 15. And so that's
Okay.
W12 by 16. Now that's even lighter than 19. That's even better. So on this page, that would be the best choice. Now I don't know if we go to the next bigger group. Let's see where we go. Here. All right. So if we go to we're getting to bigger beams now, but here 29 is the smallest one. That's much bigger than 15, but it weighs 22 pounds per foot. So I know that may have been cut off the bottom down there and push it up. So
Okay. I think I understand. I was trying to get the one closest to the S value that I found, and I was testing it and making sure it would work. So
right,
that makes more sense then.
because that's the lightest. That's the one you want to choose. Because yeah, this one is closer, but it weighs 9 pounds more per foot. So it's going to cost you a lot more money. So any question about that?
So it has to be at least equal to the S required
It's
or
got to
bigger.
be at least 15. If that was our required, it's got to be at least the required. That's why this one was really close, but not quite. Yeah, you're almost never going to find one exactly. And that one is about as close as you ever get, but it's just less than 15. So if you chose that one, and especially if you chose that one and included the weight of the beam, even if you didn't include the weight of the beam, your normal stress would come out just larger than your allowable. Be really close, but you always want to choose one at least as big as you're required. And then of those, pick the lightest one. All right, so good question.
Thank you.
All right, so again, good question. Anybody got another one? Anything else? All right, going once, going twice. Speak up, or I am going to end the session. All right, well, I'm going to stop recording and then end the session unless somebody speaks up in like the next 30 seconds or so.